Hello, and my name is Jamie. I am a lecturer here at the University of Staffordshire. I'm joined today by
Sharon. I am also a lecturer here at the University of Staffordshire. I specialise in narrative and storytelling through cinematics and animation.
and I specialise in the wonderful world of visual effects, which I often drag Sharon into. And this today is developer mode. So, Sharon, today...
Jamie.
Yes, that is me. That is I. What I am going to do is I am going to show you some VFX stuff. We're going to talk through
Fabulous.
it. But what I'm also going to be doing while doing this is I am going to be pointing towards an ethos, an approach, a learning practice, which is really beneficial for anyone trying to get not only into the creative fields, but especially visual effects within games. There's a lot going on inside of visual effects in games. There's many, many different things we do. Like, for example, me and you have taught things like Niagara particles before.
Yes, sparkles.
Sparkles. But the other, there's so many other areas you can get into as well. And the one that we're going to look at today is we're going to look into a little bit of shader programming.
Oh, amazing. So we're going to start talking a little bit, if my memory serves me right, about mathematics and starting to sort of think about how stuff works in the space.
Yeah. Okay. So sort of how we actually render things in the 3D space.
Okay. Are we going to be making something as well?
Yeah.
Okay.
Yeah,
nice.
we're going to be making something.
Cool.
What we're going to be making is actually sat in front of us already.
Oh, amazing. So we're making this.
Yeah, this. Okay. This is a weird sphere.
Well, I didn't like to say.
This is a weird sphere. It's got some glowy bits around it.
Yes,
because you requested sparkles, so I've made some sparkles. But what we're going to be focusing on is this little sphere in the center.
Okay.
Now, you'll notice that when I'm panning around it and looking at it, it is looking exactly the same from every single angle we're looking at it from.
I didn't like to say, but it is.
But that is actually kind of the idea, because what this sphere is, it is actually a sphere. It is a three-dimensional object. What we are doing is we are shading this sphere in a particular way using mathematics to create this kind of look and effect.
Okay, nice. And
Go ahead.
We're going to look at how we actually do that.
100%.
Okay, fabulous.
Yeah. This is commonly referred to as a sort of outline shader using a Fresnel approach.
Okay,
You're aware with our good friend Fresnel.
I love a Fresnel, spelt Fresnel, just to annoy people when they're looking for it in engine. So, okay, so what does, let's start at the basics, if that's okay, and then we can move on to kind of the more complex stuff.
Yeah.
What does the Fresnel do?
Cool. So I'll explain it in sort of two parts. One is the method, the method to my madness, and two is actually how we go about putting together something like Fresnel.
Amazing.
So have you ever heard of HLSL?
I have. But if you ask me what anything stood for, not a clue. So, yeah, I've heard of it, but unpack it for me.
It stands for sort of high-level shader language.
Okay.
And what it is inside of a game, inside of a 3D world that we've constructed ourselves, everything that you see, everything that you look at is a mathematical function. Okay. Because we're doing this from within a computer, and computers are mathematical function boxes of weird sort of dark magic. Okay. But they're all maths and cool stuff.
See, I can get behind the dark magic bit.
Dark magic, but imagine a lot of ones and zeros.
I can do that.
There we go. So everything that we do, everything we see in a game is maths.
Okay.
All of the visuals are mathematical as well. So how we calculate things like light, how we calculate things like the material on a box, how we calculate what things look like and how they look, and how they read. Are they metallic? Are they reflective? Everything we do is based on mathematics.
Because I guess at the end of the day, whatever we're creating in a VFX environment, we also have to think about how it's going to look in the wider game. So we've got all of these things going on and all of these considerations, which are all quite creative. We've been talking about maths, but there's a big creativity push in there as well.
There's an intersection here between creativity, as you've said, and like actual application. Yeah. And one of the things I want to point to as I'm going through this is actually I'll quickly demonstrate, because this example here
demoing
inside of m_example, I've actually gone into the material graph inside of Unreal and I've grabbed their Fresnel node.
Yes.
So boom, done. I've done Fresnel, haven't I?
Oh, we're finished.
No.
How?
Unreal Engine is famous for being jack of all trades, providing a lot of stuff that does stuff for us so we don't have to do it ourselves.
Yes.
But in an increasingly changing environment when it comes to creating the work that we do, there has got to be an emphasis on making sure that we fundamentally understand what we're actually doing in a creative field so that we can make sure we are doing that in an ethical way.
Okay.
And also a way that we can recreate it elsewhere.
Okay, that makes sense. So knowing how the node, in this case, actually works and how we can recreate it.
100%.
Cool.
It's a bit of a dramatic take when it comes to talking about things like visual effects, because we are just creating pretty stuff for a purpose. But there's a wonderful sequence in Jurassic Park by the wonderful Dr. Ian Malcolm, who you will be acutely aware of, because you've got a wonderful background in film. If you don't have
acutely aware,
go and Google it. The second you look up Dr. Ian Malcolm, you will see the very famous photo of him doing a sort of French girl pose, wide open shirt, and then you forget what the film is about at that point. But he's also the one who points to a lot of being responsible around technology in that film, because there's a whole premise of going too far with technology, which they do in the film, and that's how we get the dinosaurs. And that's how things go wrong, because trying to control technology you don't understand and trying to control things you don't understand, like dinosaurs, or in our case, shaders. In the dinosaur case, people got eaten. In the shader case, if you are trying to put together shaders and you don't understand what you've done, your worst outcome is getting stuck and not being able to go anywhere from there. So knowing how these things function and get put together is incredibly important if you want to be a professional in this field.
So I'm going to say, and let's start looking at some of this as well, instead of like sort of listening to us chat about kind of ethics. But
and Ian Malcolm.
And Ian Malcolm.
Ian Malcolm.
But it also sounds like we're looking at an approach where we do foreground problem solving as
100%,
well. So that we're not just using something that's ready made for us and going, well, it works. We're unpacking that a little bit, understanding how it works and actually understanding how we could problem solve if something isn't applying it in the way we want or working in the way we want.
Yeah.
Okay, cool.
So let's unpack Fresnel and understand how it works. First off, I'm going to delete it. Goodbye. There it goes. The only thing I've got going on in here is I have a lerp, which
Love alert.
Goes between two different colors based on an alpha. I'm not going to get too much into that because I don't have time. Let's have a think about how Fresnel actually works. So the way that Fresnel works in the real world, it's a concept based on the idea of light bouncing off of surfaces and the angles at which that happens and sort of differences in that. It was invented by a wonderful Frenchman, I believe did a lot of work with lighthouses to affect how light leaves.
Yeah, if you look at a lighthouse, that is a Fresnel light. Yes. So it's that idea of the way in which the lens is kind of shaped to reflect light in different ways.
100%. So we're thinking about angles. We're thinking about angles of light and how they sit. The way that Fresnel works in our sort of fake three-dimensional space is that the Fresnel that I just had does a sort of value comparison between two values.
Okay.
Now, the value comparison it does is it finds the angle that we're looking at it.
Okay.
So the direction we're looking at it.
Okay.
And then it will find the angle at which the plane is sitting.
Makes sense.
And it will figure out the difference between those two.
Okay.
So for example, hold up a hand for me. Hold up a hand.
Yep.
So I'm the camera. Okay. Sharon is a 3D object in a video game. She's
definitely,
3D.
Definitely 3D.
So I'm the camera, Sharon is a 3D object. So my camera is facing sort of this way and pointing towards Sharon's plane here. Now, because they are, my plane, sort of the angle I'm looking at outwards is flat on to the plane that Sharon's hand is currently sat at. They are more or less facing the same way. There's not a lot of angle of difference, is there? They're going to be the same. So the value we're going to get back from that is going to be 0.
Fair.
So we've got a 0 in terms of angle difference.
Yeah.
If you were to turn your hand away, there we go. Now, when we look at it, when I intersect with where Sharon's hand is, we have a different angle of incident. So we can take that and create that a value, which I'll talk about how we do that in a moment. But we can compare those different values when we're looking at different planes.
For it to make sense in the 3D world.
100%.
Cool.
We can do that with any plane that we see in front of us if we designate it to do that. So in front of us, on this example, we have a wonderful cylinder that I made in Blender. And what I've done is I've popped one of those lerps on again, lerping between green, which comes back if there is a value of 1, and blue, which comes back if there is a value of 0.
Makes sense.
And you get this. So the flat plane of our cylinder that's facing towards us
So 0.
is at 0. And the further out we get, the more angles we get on that, the higher up that difference value goes.
Makes sense, because if we look at the top, it's our kind of our 1.
Yeah, so we're like skimming off the top of of that when we're looking at it, and we're getting that highest value. So that's what Fresnel does inside of the engine. That's how it does. So how would we go about recreating that?
An excellent question that you're going to answer.
Yes, I am. We're actually going to start. I'm going to very quickly sort of pseudo-code it out. The way that we perceive things, or the way that we can compare things within a three-dimensional space, is the same kind of mathematics that's used to create the space. And it's three-dimensional vector mathematics. If you've not worked with vectors before, what a vector is it is a collection of values that can be used to sort of establish different information in a 3D space. So, for example, in front of us, these are named after Dragon Age characters, so I can talk about them easier.
Okay.
Vectors can be combined together with 3 different values, so an X, a Y, and a Z, to determine a 3D point in space.
Makes sense, because we're used to that when we work on identifying some stuff in beginner maths, aren't we? We're looking at the x-axis and the y-axis. Okay.
Yeah. What they do is they essentially form, or you can visualize them as a point from one point to another. If that makes sense.
It does.
So a vector is made up of 2 components. A vector is made up of a direction, and a vector is made up of a magnitude. Now, a direction is a collection of, at least in terms of 3D vectors, a collection of 3 values that are between 1 and -1. You have an X, you have a Y, and a Z. So let's say, for example, if I'm looking directly at the camera, this is my X axis. So if I'm looking directly down the X axis, I will return a value of 1. So I'm looking directly down the X axis, I have a value of 1, that's my direction. If we were to incorporate another axis into it, so let's say our y-axis, so that's our x-axis, going that way is going to be our y-axis. If I was to sort of rotate a little bit, there we go. I'm looking sort of halfway down, or if I'm looking in this direction, I'm looking sort of down X, I'm also looking down Y. So we combine those values together to figure out which direction I'm sitting in. So maybe that would equate as -0.5 on X and 0.5 on Y. I'm not exact on those numbers because I don't have them in front of me.
Well, because you haven't got something to measure your spin in with.
I don't.
But near enough.
Near enough. And then what I could do, and you can equate that as aiming half down X, half down Y. And then because we're working in 3D, we can also incorporate the Z angle as well, the Z axis even, and just angle upwards. And that third value would become another value. The other ones would then sort of
shift and change a little bit.
And you get 3 values between 1 and -1 that dictate the direction you are looking in. So that is a direction value. Awesome. That is how we equate which angle we're looking at with this vector. A magnitude is the sort of length or value or distance that vector is.
So is it how far into space
how far it goes? Essentially, yes. And that's how you make up a vector. I've got some more in-depth breakdowns in here as to how, so you can kind of see a vector being formed over here. This is Dorian the Vector, because I named it after Dorian Parvis from Fallout, not Fallout.
Dragon Age.
Dragon Age, there we go. I've mixed up my RPGs. We can kind of see, and we've also got a little bit of mathematics into here as to how you would figure out that magnitude as well. The way you do that, if you want to figure out something's magnitude or something's length, is you take all 3 components. So the X, the Y, the Z, you square those components. So you times them by themselves. You add them together, and then you find the square root of that result. And that gives you the length of that individual vector.
So that gives you your magnitude.
So that's, this is the one that you can see at the top is a fully combined vector.
I was looking at Dorian. Not going to lie.
Looking at Dorian. It's a fully combined vector, and that means those values contain both the direction and the magnitude or length.
Makes sense.
And this is some mathematics as to how we can sort of split those out. So let's say we figure out the magnitude of a vector by taking individual components. So Dorian has 4, 2, and 3 as his individual components. We can find out the length from that.
Yes.
So 5.3, 8, 5 usually
Loads
cuts
of
some
numbers.
numbers off, but I always like to include them because it looks ridiculous. And then what we can do is if we know the length of it, by going through each individual component, so the 4, the 2, and the 3, and dividing by that magnitude, we get a value between 1 and -1 of what the direction is of that vector.
So it gets very specific.
It does.
Cool.
So vectors are very powerful.
Awesome.
Because obviously I've not gone through the full maths here, but there's a blog we'll link you to where I have. In the case of vectors, you can figure out things like directions in 3D space. You can figure out distances in 3D space. You can figure out the distances between things in 3D space.
Really important.
100%, yeah. And because we are working with 3D space information, we're working with these lines that are dotted around the place. We can compare them to other 3D vectors within that space. So let me just skip through there. Don't worry about that. Let's go ahead and pop in a vector to our actual
object.
Thank you very much. My brain turned off there.
That's all right. Mine does that quite a lot.
And let's see what kind of information we can get from this. So I'm going to stick this into the lerp for now. Right now, there is nothing going on in this particular block of code. What you're looking at here is you're looking at the Unreal Engine material graph with a custom HLSL input node in. So I can use this to build a HLSL function. And what I've done is I've pulled in some information from Unreal to give us some world space locations to start comparing with.
Great.
So for example, we have the camera position.
Which is super important.
100%, that's where I was.
We are. Yeah.
And then we've got things like absolute world position, and we'll get to pixel normal in a second. But essentially, we have camera position, we have absolute world position.
So it might be just worth really quickly, because I don't know what our viewers' sort of backgrounds are. So camera position, very briefly, what is that in the world?
So that is going to be a collection of 3 vectors again. 3 values, an X, Y, or Z.
Yeah.
So that's going to be, let's say I'm at the center of the room. The center of the room is my world. I would be at world location 0, 0, 0. We are the center of the function.
We are the center of the world, obviously.
You're slightly off to my left.
I am.
So you would be at X0, Y 100, Z 0.
Fabulous.
So we've got a 3 float collection that tells us where we are in a world space.
Okay. Just makes sense for people who aren't quite down with all of the terminology. So that just gives us an idea about where this thing is in the world. Brilliant.
Cool. So the first thing we're going to do is we need to create ourselves a quick rudimentary vector.
As we do.
As we do. There's actually a neat little trick you can do. I do have one that I've made earlier because I grew up watching Blue Peter and I'm a prepared person.
Wonderful.
We can create ourselves a vector. And the way you can do that is if you have 2 world space vectors. So if you've got 2 of those 3 collections, so me and you.
Okay, me and you.
We can create the vector or the line that would be drawn between them by subtracting our start position from our end position.
Okay.
So let's say I'm the camera. If I wanted to figure out the line that's drawn between me and you, I would subtract my camera position from my pixel position. You are my pixel position in this case. So we have drawn ourselves one of those vectors we talked about earlier. Awesome.
I just quite like being, I am the pixel. I am the pixel.
And the next thing we're going to do is I'm going to start comparing some of these values.
Okay.
Now, the thing that's going to change based on the 2 values that I've talked about, such as the camera position and the world position, if we could move further apart from each other.
Yes, because things do move within games.
Things move in games.
Yeah.
So what we can do is we could figure out the magnitude or the length of that line between us and use that as a value to start evaluating things.
Okay.
A value to evaluate.
A value to evaluate.
So what I'm going to pull over is I have some code here which normalizes our value, our vector that we've made. So the instant vector we've made, by normalizing it using that kind of like timesing the individual components together and then square rooting them, I can get myself an instant magnitude.
Okay.
The great thing about using the HLSL node inside of Unreal Engine is that, or HLSL in general, is I can return any value I want.
Okay.
So I have returned for myself the incident magnitude value.
Okay.
So the value that's now popping out of this end pin at the end of my calculation is the distance between me and the objects that I have this shader functioning on. So you're the object of the shader.
I was going to say, I'm the object.
The camera.
Okay.
In this case, it's going to throw out a really big number. So what I'm going to do is...
I was going to say, we can see a change, quite a big change.
Yeah.
In it. Yeah.
So because lerps work between a value of 0 and 1, and anything you push past those values, so at 0, it's going to be red. At 1, it's going to be blue. Because this is returning if our camera distance is maybe 300 here, it's returning blue times 300, which is making it really glowy.
Really, really bright.
Very quickly, what I'm going to do is I am just going to essentially divide it down by multiplying it by 0.01. That's 1.01. Come on, play ball, Unreal. There we go. 0.01, so we're going to get some lower values in here, but what we should be able to see is now I'm far away, I've still got that blue, but if I go in further, you can see it becomes red when I'm really, really close. I might be able to make that a bit more readable if I just add one more decimal point in. There we go.
One more 0.
So I've got red when I'm really, really up close. And I've got blue when I'm getting further away. Because we're lerping between those two values. So we're getting that distance. So already we have a value we could play with. So if I went in and applied this, now I have that. What I have is the further away I am from this object, it's blue. But if I get closer, it is pink or red.
Red.
That's already something that we could use out of this. And we're not even close to sort of finishing or rounding out what we need to do to create the original effect.
Which was the Fresnel.
Yeah, but knowing that we can compare distances or we can find distances, already a really useful thing.
Incredibly useful if you think about starting to place things in an environment and they see how they're actually going to look.
Exactly. So good to know and good to be able to do.
So this is the start of our problem solving. It might not be the problem we're setting out with, but actually it solves quite a few problems if we know how to do this when we're trying to build our world.
Yeah.
Okay.
And we're one step closer to sort of solving our problem that we talked about earlier.
Yeah.
Because we need to be comparing angles.
Yes, we do. I remember that.
So we need to be able to compare two of these 3D vectors to find that angle. In this case, we've made the one that is the equivalent of me looking at Sharon's plane, because we now have a line that is drawn from the camera position to Sharon's plane.
Which is when we were doing this.
Yeah.
And we had two flat planes facing each other.
And if I have something that's drawn from here
to here,
right, I have a point where I've hit you or I've hit the plane.
Yeah.
So I would be able to then compare with the information we get from the plane itself, such as its normal or the direction it's facing, between the angle that this has come in at and the angle it's currently facing. So I then have two values I can compare from.
Right, so we've now got one value to start us off. How do we get the second value?
Second value,
yeah.
Awesome. So the first thing I'm going to do is I am actually going to go ahead and I'm going to normalize the incident vector. So the reason I got the incident magnitude in the first place is because I needed to be able to find the direction of our input.
Yeah.
So if we want to find a direction, we normalize our 3D value. And the way you do that, again, is you go ahead and you divide each individual component by of the actual vector itself by the instant magnitude.
Yes.
There we go. So I now have, because I wrote that code earlier, here's what I made earlier.
You know, it's for the best.
I wasn't going to type code on camera.
No, that's the thing.
That would be a bad idea.
It's always for the best.
Oh, if anyone's
ever
been in one of my lectures and tried to watch me type, it is disastrous. But now we have the instant direction. If I return the instant direction, it's not going to give me anything.
Sure.
It's just going to be a bit weird. Well, it will give me something, but it won't be anything that I can explain. Okay. It will be three values trying to tell us what direction it's going in. It won't read very well. But what we can do if we have, let me just see if I can find the right one in here. So we talked about normalization.
We did.
Creating the instant vector, we've done this. There we go. Normalization, we've done. Awesome. Okay. The next thing that we're going to want to do is we're going to want to start comparing some of these values.
Okay.
So for example, the way that we can compare two values is, well, there's lots of different ways we can do it. But the way we're going to do it today is we're going to be using something called dot products.
Okay, you're going to have to explain it.
That's fine.
Okay.
I've got on the screen, I've got a little bit of an explanation here. And the way that you use a dot product is essentially you can take two vectors or two 3D vectors.
Yes.
And you can multiply together their individual components, and then you can add them together.
Got you.
Which reaches these values up here.
Okay, so math actually be mathing.
Math actually be mapping.
Yeah.
So we take, these are, again, I named these after Dragon Age characters. And in this case, this top one is some Dragon Age ships of Dorian and Ironball that I quite like because they're quite cute in the game, in Inquisition. And then at the bottom, this is Caleb and Essek from Critical Role Season 2.
Okay.
Because I love those two and I look a little bit like young Caleb.
Okay.
This, again, I wrote this for a blog and needed to have things to keep people
It's just funny.
Keep people involved.
So we're going to multiply
so we say
Dorian by Ironball.
You get a great plot line.
Okay.
So if we take the X value of Dorian and multiply it by Ironball's X value, we take the X value of the Y value of Dorian and multiply it by the Y value of Ironball, and take the Z value of the Z value of Dorian and multiply it by Ironball's Z value, and then you add those together, you get a single scalar variable.
Okay.
So a single float value.
Right.
And in this case, we get 37.
Yes.
Because the two that we've compared together here are actually non-normalized vectors. So they've still got direction, they've still got magnitude combined. Now, that's great if we wanted to compare distances between, you can use that stuff. It's quite useful because you can get a value difference between those two.
Okay.
However, for our case, because we're using a lerb, we want to get a value difference between 1 and -1.
Right.
Now, if we were to instead do this dot product approach on two vectors that had been normalized or only contained their direction, we would only ever get an outcome between 1 and -1.
So between the numbers we want it to be.
Between the numbers we want it to be. So I've taken these two values here. So Caleb and Essek are two normalized values. They're very not normal in the show. They've both committed horrendous crimes, but they are quite a cute couple.
But for our purposes,
they're just normalized values.
Perfect.
In this case, by doing that same calculation again, multiplying them together, we get a value of 0.5. That value would plug very nicely into a float comparison, wouldn't it? Or a lerb, because it's between 1 and -1.
Because it's already where we need it to be.
Already where we need it to be. So let's go ahead and inside of, so over here, I've got the instant magnitude, I've got the instant direction. Now, what we're going to be doing here is we're going to be doing the final part of that Fresnel logic we talked about earlier, where now I know the angle at which I'm looking at it. I know the difference in the angle, or at least I know my angle that I'm looking at it from. And I know, because I have this wonderful thing called pixel normal world space, I also know the angle that the plane or that pixel is at. So I know which direction that is facing in world space.
So which way it's going compared to which way you're looking.
Yes, and I now have both of those together.
Great.
And what I can do if I have both those together is I can do that dot product calculation. So I've done
we're going to do the calculation we've just seen you showing us.
100%.
But for the space that we're working in right now. Okay.
So if I do that, I am taking the pixel normal, and this is how you do dot product, is I am taking the pixel normal and I'm multiplying it by the instant direction. I'm adding it to the pixel normal, multiply instant direction, and this is going through the X, the Y, and the Z, and adding them together. Same we did with Dorian, and the same we did with Caleb and Essek as well. And then what we can do is we can return that value. And when we do, what we will get, hopefully, if this has worked correctly, I've multiplied the value. Let's get rid of the multiply on there.
But that was from trying to bring everything down so we could see it earlier.
What you will get is you'll get that Fresnel approach. So we have that Fresnel approach. There we go. And that is how you would do the full run through.
Amazing.
Of that kind of approach.
So I'm going to ask, I sort of kind of know the answer to this, but as we've been talking about problem solving and creativity meeting sort of mathematics and science in a way, understanding how everything works, Is this an approach that we take when we're teaching this? Do we work through this, not this creating the Fresnel from scratch immediately or anything like that, but taking that idea of kind of there are steps to problem solving, there are steps to understanding creativity.
Yeah.
And how do we sort of try to put that together?
So in this case, one of the things we've done is, and yes, to answer your question, we do. In this case, what I've done, instead of taking, typing in, here's how you do Fresnel, and popping in a Fresnel load and plugging it in and not explaining what it's done, what I've done here in terms of you as a learner is I've exposed you to the concepts of vector mathematics.
Yeah.
I've shown you it in HLSL as well, which is an approach you can do. And I've also made sure to explain different things as we go along. So, for example, and this is where I'm going to do a cool thing, hopefully, and it will make me look cool. Let's say...
And me cool by association.
Let's say instead of... let me remember if I can do this. Let's say we take that institute magnitude again. Okay. Institute magnitude again. And we return that. And instead of having this be a shader on an object, let's have this be a post-process shader.
Okay.
So what a post-process shader is it's a material that essentially works across the entire screen for us. So instead of evaluating like distances between, instead of evaluating an individual object, this is going to go by every single individual pixel on the screen. So what we can do is we can take in the sort of, let's say we wanted to figure out the distance between the camera position and just outwards.
Yes. Okay.
So we're working with pixel normal still. And let's say this magnitude is now returning to us a value of, it's going to return any value between every single individual pixel and what's underneath that pixel. So we're no longer working with a single object. This is doing it everywhere across our entire world.
All the things, yeah.
Which means we can make we can ask some bigger questions. So let me just get the original scene texture. And what this is what the scene looked like before I started doing weird stuff to it. So if I plug it in, you will see the world.
There's the world that we know so well.
Because I need post-process input 0 instead. There you go. So we've got the world that we've seen before. Awesome. So we've also got this information down here, which is how far away we are from the camera. So let's grab our lerp again, and let's go and grab the color for A and stick that into A, and anything above that's going to be B. So this value here is obviously working in world units. So we're currently like 500 away, which means that those values are too big to go into a lerp. But let's say I wanted to see all of the values below 500. If you divide 500 by something, if I, let's say, divided 500 by 500, what would I get?
1.
0. No, actually, 1. Sorry, I apologize. You're right.
The math's been mathing today.
Yeah, you would get 1. Sorry. But also all the values below that would become under 1. So if we are dividing 400 by 500, that would equal out, I believe, 0.8. So that's going to fit nicely into our lerp. So what we can do with that is we can use directional information like we learned from our Voronoi, Fresnel even, I'm using the wrong French terms.
Jamie also loves the Voronoi.
I like the good ones. They're very cool. What we can do is we can establish almost like a fade distance by lerping between a post-process input 0, and which is just our worlds, however it is default, and 0, which is nothing. And by lerping between that, we're getting the values from the camera to the instant it's hitting. If I go ahead and pop back into our world, it's going to break that because obviously that's not how that works. I'm going to go ahead and find my post-process volume.
But I think something important to kind of point out is that at this point, Jamie's kind of just experimenting and showing us some stuff in Engine. But the other thing is to not panic when stuff doesn't immediately show up in Engine, when you're actually kind of working with nodes and working with VFX, working with anything really in Unreal. There will always be a reason, and it will always be something that you can, problem solve and figure out.
Yeah. So for example, it was very dark just then, so I'm just going to make my distance that I'm looking at a bit higher for this demo. So what I've done here is I've taken that same magnitude information that we figured out while we were trying to figure out a different problem.
Yes.
And I've applied it as a shader in world. And what this is doing, instead of on the individual sphere doing the evaluation, it's doing it across the entire world based on my screen space. So it's looking from where my camera is and looking to a point, going, how far away is that? If that is beyond the 3000 multiplier, shade it dark. If it's not, pretend it's post-process. And I have something that will shade my world in a cool way. And I know that, and this is where I'll wrap up, because I have experimented and learned how these systems have worked. And I've not just used what was given to me. By understanding vector mathematics and by understanding HLSL, I have a more power as a visual effects artist and a material artist to create the kind of shaders that I want, because I have more of an understanding of how the world looks underneath. And that's kind of my core message.
That's amazing. Yeah. And I've not seen you do this before. But no, you've not done this before. But this is extremely cool. But it's that problem-solving ethos. It's like, I need to know something. I know some basics to make that happen. Yeah. And then I'm going to actually kind of extend that and make it happen in a different way and get a different result.
So if you're looking to become a games developer, if you're looking to become a visual effects artist, technical artist, remember that imagination has no bounds as long as you give it the right fuel. And that is where I will end today's episode.
Thank you very much. Mode.
And that was developer mode.